So up to this point, all of the examples that I gave regarding EDTA titrations were of the sort of simplistic form, where we didn't have to consider these parallel reactions that might occur. And so we talked about calcium because the convention for EDTA titrations is that we think about the dominant form of EDTA as this Y4 minus. And in order for that to be true, we do these titrations at pH in excess of 10. Problem is that at pHs in excess of 10, the hydroxide concentration goes through the roof, right? You've got lots of hydroxide. Metals love to bind with hydroxide to form insoluble products. The problem with that is if this is occurring as a side reaction, it's depleting the apparent concentration of metal in the solution. So when you're doing an EDTA titration, you've got your beaker, and inside that beaker you've got your metal, and then you're dripping in your EDTA point by point. You may get this curve, that looks like this, and it's this nice titration curve. But at equivalence, when you're trying to figure out exactly then what the concentration of the metal ion is, which is the whole purpose of most EDTA titrations, is to figure out what the concentration of the metal ion was, some amount of that metal ion will have been used up already and precipitated out as solid in the bottom of the beaker. And so your estimate via the EDTA titration will underestimate systematically the true concentration of the metal. So what we do then, by we I mean chemists, I don't really do this very often, is we add a new auxiliary complexing agent to the system that complexes out the metal more strongly than the hydroxide, but less strongly than the EDTA. And so you end up having the metal bound up maybe with something like ammonia. So you might have an amine complex. This number is relevant right now. It will be relevant here in a second. But so that means instead of forming these insoluble hydroxides, everything is solubilized by the fact that you form these aqua or aqueous amine complexes. And but the EDTA can still swoop in here, and by EDTA I mean the Y4 minus, because that's what we're considering the equilibrium for, and still grab onto that metal ion. And so your choice of auxiliary complexing agents are really the same as what we started with at the beginning of this chapter. You've got really all of those different complexing agents. Ammonia is a really good one because ammonia has a stronger binding affinity to metals than hydroxides do, which is useful in aqueous solutions. And so often what you'll see are EDTA titrations of hydroxo-prone metals, things like zinc or iron, etc. Those things end up wanting to precipitate out as the hydroxide solid, so we use ammonia in those cases with EDTA. But the problem is then that means now you're complexing your metal with another complexing agent. Just as an aside, these complexing agents are also called ligands because they're mostly Lewis bases that can come up to a metal positive ion and donate a lone pair to it and form what's called a coordinate bond. So if you go on to take Chem 275, or you already have, you know all about this process, but you don't really need to understand the exact mechanism because it's pretty easy and doesn't take that long to understand. This is pretty much it. But these occur in equilibrium. So because your metal is now going to be bound up by ammonia, then we have to account for the fact that only some small, even smaller fraction of the original metal is going to be in its free state when it's in equilibrium with Y4 minus. And so this expression, normally we'd have the conditional formation constant where we'd adjust for the fraction of Y4 minus. Now we also need what we call a double conditional here, or a K double prime, where we account for the fraction of metal that's not bound to the NH3. So there's just an added step. It seems complicated, but it's really not. I'll walk you through the steps. So in order to understand the fraction of the metal that's not bound, we need to first understand the fraction of metal that is bound, meaning what is the metal ligand equilibrium look like? Well, that depends on the ligand, of course. So in this sort of nomenclature, we're calling the metal M, and we're calling the ligand L, of course. And the simplest sort of binding equilibrium you can have is just one ligand molecule coordinates or binds with the metal, and so you end up with some Ml complex, and that's going to be dictated by that first equilibrium constant K1. And let's just assume that this metal can only take on two different metal ligand equilibria, so it can also bind to two equivalents of that same ligand to form this new complex, Ml2. So there's two ways to write this, and I foreshadowed this back in chapter 6 video. So go back there if you want to remember exactly how I set this up. But essentially, there's two different ways to write the equilibrium constants here. We can either write them in stepwise formation, or we can add them up all at once. And so, for example, this first step is pretty easy because you're adding just one equivalent. So the stepwise equilibrium constant is the same as what we call the cumulative constant. Cumulative here, we use the beta form. So beta 1 is the equilibrium constant for adding all of the ligands to it at one time for that step. But this step is only adding one, so that's coincident with K1 in this case, which is equal to the equilibrium that we're used to. That would be ml as the product divided by L times M concentrations. But for the second step is a little bit different because we're adding two equivalents. So that's actually two successive steps in a row that we're accounting for in one equilibrium. So in other words, if we were to think about this stepwise, we would actually have ml, because that's after one addition, plus the next L, next ligand gives us ml2. That would be the actual intermediate step here if we're talking about the stepwise formation, and we would consider that K2. But when we're talking about cumulative equilibrium constants here, then we're only considering both steps simultaneously, and so we would write that as beta 2, and in that case it's really adding both steps together, where you have M plus L plus ML plus L, and then that sums up. That's the same when you add two expressions together. That's the same as multiplying its equilibrium constants. In this case, you're multiplying K1 and K2, and that gives you then the concentration of the Ml2 complex divided by M concentration L, and then the key thing here is that this gets squared because of the 2 in front of the ligand. And we could keep going if you had a metal ligand equilibria that you had 3 ligand equivalents or 4 ligand equivalents. For this simple example, we're going to assume this ligand can only be added twice, and it stops at the Ml2 complex. So remember, the original impetus in doing all of this is because we wanted to figure out, well, how much of this M here is actually unbound. So you've got a bunch of ligand present, you've got this L swimming around in solution, you've got M, you've got all these equilibria that are occurring. Well, how much of M is not bound at any given moment in time? We need to know that, because if we're then adding some other ligand like EDTA, it's reacting or complexing with the unbound form, at least in the equilibrium expression. So that's what we're trying to figure out. The shortcut to that, again, would just be to determine what fraction of M is unbound. And we know that pretty easily because we've done this a lot now. The fraction is just the alpha of M, and M here being the unbound M. So that's just the metal that's floating around, not complexed by EDTA or the ligand. That's just going to be M, whatever the fraction of M is, or the concentration of M is, just floating in solution, divided by M total. And by M total, I'm talking about all of the different forms of M, including the forms of M that are bound, ML and ML2. So what we can do is, we don't know what M total is, but we can get there. And so what we're going to do is deduce a form, an explicit form of alpha M that becomes useful to us. We start that by just computing a mass balance equation, which is really intuitive, where the m total, as I just mentioned, has to be equal to all the forms of m, which are the free form of m plus plus ml plus ml2. Those are the only three possible forms of m in the system. So that's what m total is equal to. But what we want to do is get m total in terms of things that we know, and we don't know all of these species. That would defeat the purpose. That'd be too complicated. We'd have to solve everything. So what we can do is rearrange, or the first step we can do is rearrange the equilibrium expressions, these things that are written in red, in terms of ml and ml2. And so what we'll do is actually solve this first beta 1 expression for ml and then substitute that in. And if you do that, what you get is, let's see if I have this written down, you get beta 1 m times L. Okay, that's easy. So what we're going to do is take and solve for this, and then we will substitute it there. And then similarly for the beta 2 expression, we'll take and solve for this, and then substitute it there. And so what we'll end up with is an m total that is in terms of things that we know. So the m doesn't go away because we didn't substitute that out. The first one is beta 1 m L. And then the second one, after solving that, would be beta 2 ml squared. Okay, so at this point, then we can just grab the m's out of this, so pull those out. So that would equal m here, and then that would be 1 plus beta 1 L plus beta 2 L squared. Okay. So we're getting close there. So now, remember, all of this is still equal to the total concentration of M. We just changed the terms here so that they were in terms of the concentration of M and L in constants. So we're going to take this, because this is total, and we're going to resubstitute it in for our original alpha M. So alpha M now is equal to M over m parentheses 1 beta 1 L plus beta 2 L squared, close parentheses, and then you can see what's coming here. That m goes away, and we're left with the final form of alpha m, where alpha m is going to be 1 over 1, that one, the second one that goes away. So that's 1 plus beta 1 L plus beta 2 L squared. So this would be the generic alpha fraction of unbound m. That's what this means. So unbound, it's just floating around, hanging out, happy in solution. It's not complex by anything. That's the fraction of it that's floating around as a function of the first cumulative constant of formation, which we can look up in the back of a book, and the second one, and then the only thing we need to know is then the ligand concentration that we add to solution. So this is for when you have a ligand that can form two successive complexes with your metal. So in this case, that was Ml and Ml2. Not all ligands are created equally. Some can form 1, some can form 5 or 6. So we need a generic expression for this as well. So the generic expression here would be, let's do this in blue. The fraction of m unbound is going to be, we're going to need a lot of space here, 1 over 1 plus beta 1 L plus beta 2 L squared plus beta 3 L to the third, etc., where we have then up to however many complexes that can form n. So we have beta n times the ligand concentration raised to the n. So this would be our generic expression to compute the fraction of m that's unbound. So just a reminder, the whole reason why we're computing this is ultimately we're trying to get to the metal being added to EDTA to form that EDTA complex, but we need to know how much of the metal is there in the first place, which is where this comes into play. Remember, we also are going to adjust the Y4 minus concentration by its fraction that's pH dependent. So we're going to have two alphas here in the system to compute. So that gets us sort of to our final punchline, which is in this expression, then you're going to be computing this K double prime F, where the double prime is going to be the original formation constant, and by formation constant we're still relating to this formation constant, so formation with EDTA, but we're adjusting the free metal concentration first by what fraction of Y4 minus is present. This would give us our normal K prime or conditional KF, but then we're also going to multiply it by the fraction of metal that's present in solution unbound by the auxiliary complexing agent. So really this little thing here is the only difference that we're adding to the system.